On to today's November 4th OARS seminar. Today we're very happy to have Arian Nadjimzadah from UCLA, who's going to give a talk on Bourgain's condition, sticky Kakeya, and examples. Yes.
Okay, thank you very much for inviting me. I'm honored to be at the seminar. So I'm going to discuss some curved variants of the Kakeya conjecture, which are related to a generalization of the restriction conjecture. This is known as Hörmander's oscillatory integral problem. Before we get into that connection, I need to tell you about restriction, Kakeya, and how they're connected. So let's begin with the restriction conjecture. Okay. So this is a fundamental question about how you can restrict the Fourier transform of a function to a curved surface like the paraboloid. This is our most common model case. So the modern way to state this conjecture is through its dual extension version. So I'm going to write it that way. So in the extension form, we take a function f supported on the paraboloid, and we define the following extension operator, where we take a Fourier transform with respect to f on the paraboloid. Okay. So f was supported on a n-1 dimensional object. Now EF is going to be supported on a n-dimensional object. Okay. So the conjecture is that E satisfies the following LP bounds. LPRN over here. And one way to write it is with L infinity on this side. And the conjecture is that this holds for E bigger than 2n over n-1. Okay. So this is fundamental question about the Fourier transform, as I said, and it also has many connections to number theory, PDE, combo, the list goes on. Okay. And it's also a model case of more general oscillatory integral operators, which I'll discuss. Okay, let's outline some of the progress on this. The case n equals 2, this was, we call the 70s classical. This was known to Stein in the early 70s. And the case n at least 3 is still quite open. But there's been some exciting progress due to many authors, but I'll point out the progress due to Wang and Wu in 2024, where in the case n equals 3, they managed to not get p bigger than 3, but they're approaching p bigger than 3, 22 over 7. Okay. So the progress on the restriction conjecture due to Wang and Wu and many other authors comes from understanding the geometry of the wave packets. And the wave packets are neighborhoods of straight lines. So this is connected to the Kakeya conjecture, which I'll describe to you. Okay. So we call K and Rn a Kakeya set. If it contains a line segment in every direction. the conjecture is that Kakeya sets have full dimension. So Kakeya set in Rn will have dimension n. Okay. And as is often the case in this field, we discretize our problem. So we're usually thinking about, well, instead of a set of lines, a union of lines in every direction, we think about a union of delta tubes, collection of delta tubes in each delta separated direction. Okay. So in this case, we ask for estimates of the form, showing that the union of tubes is not too small. Let me tell you, sorry, I said delta cubes, delta tubes. These are just, draw a little illustration. Length 1 by radius delta cylinders. Okay, and at the discretized level, the Kakeya conjecture asserts that this union of tubes is not too small. We can't say it's at least a constant. It needs to decay in delta because of the existence of measure zero Kakeya sets, Sokovich sets. Okay. So we're interested in this problem in a large part because, well, first, it's a classical result that the restriction conjecture implies the Kakeya conjecture. And we're slowly understanding how to turn incidence type information between delta tubes into progress on the restriction conjecture. So this is very active in this direction. This is really why the progress of Wang-Zahl is so exciting. Okay. Okay. So let's discuss the similar progress for the Kakeya conjecture. We're seeing a theme here, in n equals 2. This was known to Davies since the 70s. And very excitingly, this is now known in n equals 3 due to Wang and Zahl in 2025. But n at least 4 is still open. Okay. Now I'd like to tell you in some very broad strokes the technique of their proof, since it'll play a role when we study the curved versions later. Okay. So the idea is to first prove a so-called AD regular case. This is a common theme in harmonic analysis recently. And for Kakeya sets, this is known as the sticky case. And then reduce general Kakeya, or general configurations of tubes to the sticky case. Okay. Now, what does the sticky case look like? Well, a Kakeya set is sticky. This was the definition used in a paper of Wang and Zahl in 2022, which is the first of 3 papers in this breakthrough. In this formulation, a Kakeya set is sticky if the tubes are packed very tightly together, in the sense that tubes which are close together in direction must also be close in position. So here we have 2 tubes which are close in direction. I'm very much not drawing the entire Kakeya set. And we have 2 other tubes which are close in direction. And it has the property, this multi-scale property, that when you cover the tubes by, cover these delta tubes by fatter tubes, the collection of fat tubes itself is a sticky Kakeya set at a coarser scale. And when you rescale each fat tube into the unit cube, you get another sticky Kakeya set inside of each one of these rescaled fat tubes. Okay. Taking delta to zero, this notion can be captured by the packing dimension of the set of lines in the Kakeya set being as small as possible, right? It's at least n-1 because we have the set of directions has dimension n-1, and this is saying that it meets n-1 exactly. Okay. So then general Kakeya, well, or I guess a non-sticky case would be two tubes which are not quite parallel, but are far away in position. We have two tubes which are close in direction, but are far away in position, so that when you cover them by fatter tubes, you get parallel tubes. And this was, just say Wang-Zahl 22 was used for this part, and this is what happened in, this reduction was used in Wang-Zahl 25. Okay, so let's keep this paradigm in mind while we move on to discuss the Hörmander oscillatory integral problem, which is a generalization of restriction. And when I say restriction, I mean the extension operator form of it. Okay. So Hörmander's oscillatory integral problem. Okay. So we replace the phase function in the oscillatory integral operator defining the extension operator, defining the extension operator with a more general phase function, which we call a Hörmander-type phase function. And this is a phi taking inputs x and c in Rn and Rn-1 respectively, which satisfies the following non-degeneracy conditions, which makes it look roughly like the extension operator to first order. So the first is that this has full rank. This matrix, this n by n-1 matrix has full rank n-1. And after defining a Gauss map, then we have the following curvature condition. And this vector field applied to this Hessian gives you a matrix which is non-degenerate. Okay. So now we can define the Hörmander operator. So we start with f supported on Rn-1, same dimensionality as Pn-1. And we define the following operators T lambda, n-1 e to the I lambda e over lambda f of c a x over lambda c dxc. Okay, let's unpack this for a second. This a is just a bump function. And this lambda is useful for scaling reasons. Okay. So by doing a change of variables in the extension operator, you can recover this restriction case. by taking this one special phase function, t c squared, where we write x as x prime comma t, vector in Rn. Okay. So this is, we now have a very natural question, which is, for which phi satisfying these Hörmander conditions, phi which is Hörmander type, do we have a restriction conjecture type estimate? T lambda f, now p, and lambda to the epsilon f in infinity of Rn minus 1. For the same range, p bigger than 2n over n minus 1. Okay. Cool. Let's once again follow the same theme as above. You can probably guess that n equals 2 was also known since the 70s. This is always true for any Hörmander type phase function. And this is due to Hörmander in the 70s. Okay. Then Bourgain came along in the 90s and proved that this estimate star can in fact hold for generic phis. This was quite surprising at the time, I believe, as Bourgain does. In the 90s, Bourgain showed star fails for a generic phase function phi. Okay. This was later extended to all dimensions, at least 3, in a very nice paper by Guo-Wang-Zhang. I'm going to discuss other aspects of this paper as we go along in 2022. Star fails for generic phi. Okay. You're probably wondering what these generic phis are and how we can avoid them. So let me tell you that first part first. The generic phis this was formulated by Guo-Wang-Zhang. These satisfy the following property. For some xing c in the domain of the phase function phi, this vector field applied twice to this Hessian is not a multiple of this object we saw in the Hörmander-type condition. This vector field applied once to the Hessian. Okay. All right. Now the following definition presents itself. We'll say that phi satisfies, well, Guo-Wang-Zhang would say this. Guo-Wang-Zhang said that phi satisfies Bourgain's condition. Bourgain's condition. If for all xing c, this matrix is a multiple of this other matrix. Right. So we should expect that Bourgain probably found all of the potential issues So we make the following conjecture. This was made in Guo-Wang-Zhang, which we'll call the Hörmander dichotomy conjecture. Which is that star holds if and only if phi satisfies Bourgain's condition. It's a star holds for phi if and only if phi satisfies Bourgain's condition. Okay. As you'll recall, star is this main question. Okay. So the restriction operator in particular, or the extension operator in particular satisfies, its phase function satisfies Bourgain's condition. But also, there's this question called the Bochner-Ries conjecture about the summability of Bochner-Ries means. It's a fundamental question about Fourier series. And it turns out that if a certain operator which satisfies Bourgain's condition satisfies our estimate star, then we solve the Bochner-Ries conjecture. So this conjecture unifies restriction and Bochner-Ries. Okay, so fairly important. Now let me tell you about the progress that Guo-Wang-Zhang made and some issues I see in making further progress. And then after that, how I try to alleviate some of these issues. Okay, so progress. Due to Guo-Wang-Zhang, they gave improved estimates approaching star when phi satisfies Bourgain's condition. Oops. Phi satisfies Bourgain's condition. And this, again, relied on the understanding, to some extent, the incidence geometry of the wave packets corresponding to this operator. What they really used was the polynomial method. In a difficult way. Okay. Of course, one direction of this conjecture is true because the direction that if phi fails, or if phi fails Bourgain's condition, then star cannot hold. We know this is true now. Okay, let me tell you about some issues that we need to resolve in order to make further progress. So the first of these issues is that we need some better understanding of the incidence geometry of the wave packets corresponding to these operators T lambda. That is to say, we need a better understanding of the curved, some corresponding curved Kakeya problems. And it would be nice to see a more direct connection to the restriction case. Are there any kind of reductions we can make from the Bourgain case to the restriction case? And also, as more evidence that this Bourgain condition is the correct one, it turns out to be invariant under diffeomorphisms in X and C separately. And we would hope for this because this estimate star as you can check, is also invariant under such diffeomorphisms. But the calculation to show this diffeomorphism invariance seemed rather miraculous to me and was rather long. So it would be nice to have a direct explanation of diffeomorphism invariance for the Bourgain condition, which I'll just write as bcond here for brevity. Okay. So what I'll do now is tell you about the wave packet geometry of these operators T lambda and curved Kakeya, and then I'll tell you how I give some partial answers to these questions. Okay. So wave packet geometry of T lambda and curved Kakeya. Okay, so the wave packets are neighborhoods. After doing that calculation, you can see that they're neighborhoods of the following family of curves. These are X, the set of X satisfying this equation, sitting inside Rn. So here's where Hörmander's conditions come in. The first Hörmander condition, which is the non-degeneracy of this mixed Hessian in X and C, guarantees that these are curves. They're curves by the first Hörmander condition. Okay. Let's take the special case of this phase function here, which I said recovers restriction. When you consider this phase function and do a quick calculation, you see that LXCV is a line which hits the xn perp plane at v0 in direction xi, 1. Okay. An analogy with this, we might guess that xi is the correct generalization of direction, and it turns out that it is the correct generalization of direction by using the Hörmander-2 condition. So xi is the correct generalization of direction. And this is by computing with the Hörmander-2 condition. Okay, so now we have curves and we have directions, so we can define Kakeya sets. So we'll say K in Rn is a phi Kakeya set if for each direction xi in some small open set, there exists a v such that LXCV intersect a ball where we don't care about infinite lines of infinite length or curves of infinite length, such that LXCV intersecting some fixed ball is contained in K. Okay. Right, this can you get classical Kakeya by just taking these lines up here. Okay. So we have another, it follows the same arguments of why restriction implies Kakeya to show that having the estimate star implies that curved Kakeya sets have full dimension. This is a classical application of Khinchin's inequality. And just like for the restriction to Kakeya case, we're slowly understanding how to move our way back to understanding Hörmander's problem. Okay.
Arian, I think there's a question in the chat.
Oh, I don't see the chat. Yes, LCV is a curve. In the special case, yeah, let me tell you. So this is the special case of restriction. Thanks for the question. Okay. Great. Okay, so given this classical implication and the Hörmander dichotomy conjecture, we should of course conjecture that if phi satisfies Bourgain's condition, then phi Kakeya sets have full dimension n. Maybe I should say Kakeya sets in Rn have dimension n. Okay. Of course, the phase function phi implicitly includes this n. Right? Okay, and you can similarly, just like we delta discretized Kakeya sets, you can similarly delta discretize phi Kakeya sets. So you get delta neighborhoods of, you get delta tubes, curved delta tubes instead of straight delta tubes. Phi Kakeya sets. Okay. I'll pause for a moment if there are any questions. Okay, seems like people are fine. Okay, now I can tell you about my equivalent characterization of Bourgain's condition, which works at the level of curves, is written completely in terms of geometry and helps to resolve these questions I asked above. So characterization. By the way, this will all appear in on the archive shortly. So I show that phi satisfies Bourgain's condition if and only if the following holds. For each fixed central curve, you write L xi naught v naught, there is a local diffeomorphism f from Rn to Rn, such that for all delta, we have the following picture. You look at the delta neighborhood of your curve L xi naught v naught, or I should say the square root of delta neighborhood. And then you consider all of the family of delta neighborhoods of curves which sit inside of the square root of delta tube. So what are these curves? They're just the xi and v, which are within square root of delta of xi naught and v naught. Right? This parameter xi and v gives us a way to measure distance and packing inside of our family of curves. So there's a diffeomorphism from this picture. So this is length 1. to this picture. A family of straight delta tubes inside of a square root of delta tube. Again, length 1. With the property that it preserves the direction separation, in the sense that if I have curves on the left, which have different x's, then they're sent to lines on the right with different directions. Okay. So here we have a direct connection to restriction. And I'll explain this. It's transparently diffeomorphism invariant in X and C separately. Let's see why that's the case. If you compose phi with a diffeomorphism in X, then that's the same as just composing this function f with a diffeomorphism. And you compose it with the same diffeomorphism for every fixed xi naught and v naught. And when you compose phi with a diffeomorphism in xi, you get a family of curves where you apply some diffeomorphism in xi for that xi direction parameter. And if you apply diffeomorphism to separated points xi, you're still going to get separated points c. Okay. So no calculations required to see that. So we can use this characterization to better understand the incidence geometry and prove some steps towards conjecture, Hörmander dichotomy conjecture at the level of Kakeya sets. Okay. So using this, the multi-scale self-similarity of sticky Kakeya sets, and a actually fairly quick induction on scales argument, you can prove that sticky Kakeya in Rn, by which I mean sticky Kakeya sets in Rn having full dimension, implies that sticky B Kakeya sets in Rn have full dimension. Of course, for B satisfying Bourgain's condition. Okay. And using just the 2022 result of Wang-Zahl, you could use the 2025 result if you'd like to. This is in particular true in the n=3 case. Okay. I didn't quite tell you what sticky phi Kakeya sets are, but maybe you can gather from the picture for lines. But the parameters xi and v give us a way to measure how packed together curves are. So you should imagine the same picture except with curves. Okay. So if you like the packing dimension of the family of curves of our curved Kakeya set K, taking delta to 0. E is n-1. Okay. All right, so this tells us we can just let everyone go prove results for sticky Kakeya sets in Rn, and we automatically get them for this more general conjecture. But then, of course, there's a question of, well, is it as easy to prove the general, the sticky reduction? So what are the general Kakeya set of curves? Well, you might have two curves which are close together in the direction C, but far away in position. Okay. So how much more can we reduce the Bourgain case to the restriction case? Okay. The answer is probably we can't reduce it so much. Probably not by much. Let me tell you an example which demonstrates this. Okay. For notation, it's a slightly ugly example, but it's the easiest one that I could write down. Let's write x as x prime, xn minus 1 comma t, vector in Rn, and c as x prime, comma cn minus 1, vector in Rn minus 1. Okay. Now the example is, which satisfies Bourgain condition, x prime dot c prime plus t squared over 2 c prime squared plus a log of a secant of a t c n minus 1 plus xn minus 1. Okay. So this satisfies Bourgain's condition. You should be a bit careful to take t not equal to 0, though. Do it away from t equals 0. Okay. Now, what's the issue with this example? But you can find a central curve so that for any, however small you take delta, the delta tubes in the delta 1/4 neighborhood of this curve, showing some delta tubes, are not diffeomorphic to a family of lines, regardless of direction separated or not. Okay. This is length 1. Again, delta to the 1/4 times length 1. Okay, so you can't do much better than the characterization I wrote down, barring maybe delta to the 1/3 radius tubes. Okay. In particular, the arguments for the general, the sticky reduction of Wang and Zahl from 2025, they use scale differences significantly larger than delta to delta to the 1/4. So you need some new arguments to handle a general to sticky reduction, which I don't think, because of this example, can be reduced to the restriction case. I'm currently thinking about techniques for the general too sticky reduction. Okay. Are there any questions? All right, that is what I wanted to